As you can see from the title of this lesson, this tutorial is about looking at electrons and light when they behave like particles. And to this point, we tried to answer a very fundamental question that we were bringing up earlier in the chapter, which was, why is it that electrons do not crash into the nucleus because of the opposite charge attraction? Electrons are negative, the nucleus is positive. In theory, the electrons should crash into that very dense, positively center. And the first part of the answer to that question is that electrons must behave as waves. They must have frequency and wavelength because waves do not feel forces of attraction. So light, we know, can behave as a wave. It doesn't feel force of attraction or get bent, right, in a field of magnetism. And what we found out is it can diffract and deflect, and there's many wave characteristics to light and electrons. The catch with the electron argument is this. We know that electrons show forces of attraction, right? Stemming all the way back to Rutherford's gold foil experiment, where your positive particles got bent and things like that, and electrons can be deflected in a cathode ray tube around things. So we know that they feel some forces of attraction and repulsion. So the wave idea explains why they don't crash into the nucleus, but now we need to talk about how it is that electrons and light can behave as particles. If we're going to do that, we need to discuss an experiment. Right? And the experiment that is of extreme relevance to this conversation, right, is called the photoelectric effect. You'll be able to find definitions of these things in the handout section, so go ahead and print those out if you've yet to do so. Right? But the photoelectric effect refers to the emission, right, of electrons from the surface of a metal when light is shown on the metal. Believe it or not, this is one of those discoveries that was actually being conducted to prove that light was not a particle. Right? The idea behind the experiment that is the photoelectric effect is this. You take a piece of metal, and if we choose a metal off the periodic table, say we choose tin, Sn. Tin has a plethora of electrons, right? Tin's atomic number is 50. That means each atom of tin has 50 electrons. So the surface of this metal is covered with electrons. The idea behind the experiment was this. If we take light and we shine light down onto the surface of the metal, right? If light behaves as a wave, right, the wave should just reflect off the metal or pass through the metal if there would be space for it to do so. So what they expected to happen when they did this was they expected light to shine on it, and they had a detector waiting to see if any electrons would be ejected from the surface of the metal, and they didn't expect any electrons to be ejected. Well, what they found out when that happened was, in fact, electrons were ejected. And the fact that the light was able to strike the electron and displace it is a very distinct property of something that is a particle. Right? Imagine I have two tennis balls. Right? If one tennis ball slams into the other tennis ball moves. That's because they're both particles. If one of them were just light shining onto the tennis ball, right, we would think that the light just hits it and bounces off. But what they found was, if they made the light strong enough, the light would knock the tennis ball out of my hand. That is the photoelectric effect. So what happened is they needed to explain why it is that they think light was able to do that, and the only logical conclusion was that light can behave as a particle. And if light is able to behave as a particle, the idea is that if it can behave as a particle and as a wave, why is it that electrons cannot do the same thing? The only other thing that contributed to this is the amount of light. At the beginning, a weakly light bulb, something like a 60-watt bulb, wouldn't eject electrons. But a 100-watt, for instance, would eject electrons at a specific rate. So there seemed to be a threshold, so to speak, that you had to surpass to get an electron to leave. And so that led into the idea that there's not only an amount of energy that ejects an electron, but a specific amount of energy. Right? And the person that really contributed to explaining this was a scientist by the name of Max Planck. Right? And Max Planck suggested that there was a specific amount of energy. He suggested there was a specific amount of energy needed to eject my electron, and if I meet that amount, the electron will be ejected. Right? So the idea is that he suggested that there's a specific amount of energy needed to eject an electron. He gave that amount of energy a name. He called it a quantum of energy. So don't get caught up in the word quantum thinking that it's entirely difficult or anything like that. Quantums of things are just specific amounts of things. So a quantum, right, of energy is a certain number of energy needed to make this happen. Right? Quantum mechanics relates to certain amounts of energy that make things happen. Quantum physics, right, is a field based entirely around looking at those amounts of energies. Right? So he defined a quantum as the minimum amount of energy that can be lost or gained by an atom. Right? A quantum of energy, like I said, is a specific amount that the metal needs to gain to eject an electron. So whatever that minimum amount is what we call a quantum. Now, quantums can vary from different elements. The amount of energy needed to eject a tin electron could be different than the amount needed to eject a silver electron. But the idea is this, is no matter what sample of tin that I get from across the world, the quantum of energy for tin is one set number. The number may be different for silver, but every silver atom has a certain quantum of energy that it needs. So he evolved this into an equation that links energy to these quantums to what we're going on. And this is the equation he came up with. E equals hv. No surprise given what we've been talking about. E refers to energy. And energy is measured in joules. V, we've talked about that before. V is frequency. And if you remember, frequency gets measured in hertz. And then lastly, h, right, is a constant, much like the constant for c equals lambda v. C was the speed of light. H is something known as Planck's constant. And it also gets a specific number. It is 6.626 times 10 to the negative 34th joules seconds. And so Planck's constant, like 6.626 times 10 to the negative 34th joule seconds, is always the same. So now we have two ways to look at our electrons and light. As particles, which have energy, which have frequency, right, which can displace things, and separately as waves, right, which have a different equation, C equals lambda v, which have frequency and wavelength and relate to the speed of light. Just like we were able to solve problems using this equation, we'll also be able to solve problems using this equation, and I wanted to look at some of those as we go. First question I'd like to look at says this: what is the energy in joules of a quantum of radiation, right, that has a frequency of 6.7 times 10 to the negative 15th hertz? And so the idea behind it is this: if we know that this frequency ejects an electron, how much energy is that worth? The good news is we use the same system for solving these types of problems as we did for these types of problems. That system remains the same. I look at my number and I decide what it is. 6.7, 10 to the negative 15th hertz. Hertz measures frequency, and it says so there. So we know that V is equal to 6.7 times 10 to the negative 15th hertz. I'm all out of numbers, so the next thing I do is figure out what does the question want. What is the energy in joules? So I'm looking for energy. Now I have two equations to choose from. I have E equals hv and I have C equals lambda v. So I need to decide which equation is more appropriate for what's going on. Well, I see a V, which they both have, but I also have listed E, and only one equation possesses the E. E equals hv. Again, H is there, but it's no big deal. It is Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds. From here out, it's just like we used to solve the last problem. Get the thing you're looking for by itself. We want energy. Energy is already by itself, so we can just plug in. H was 6.626 times 10 to the negative 34th joules times seconds. V, 6.7 times 10 to the negative 15th hertz. Remember, hertz is the same as 1 over seconds, so seconds and 1 over seconds can cancel, which would leave my answer in joules. From here out, it's a math problem. So I get my calculator. 6.626 second E negative 34 times 6.7 second E negative 15. My calculator says 4.439 times 10 to the negative 48th. Watch for your sig figs. 4 here, 2 here. I only get 2. So 4.439, right? 4 counts, 4 counts. A 3 will not round the 4 up. Means 4.4 times 10 to the negative 48th joules. And do not be alarmed by the magnitude of the exponent in the positive or negative fashion. You have to realize electrons are very, very, very tiny. So it will not take an extraordinary amount of energy to displace them. Right? In my hand, if I had a sample of tin, I would be holding billions and trillions of electrons. Right? And if light can knock that out, it doesn't take a whole lot of light to do so. Second question. What is the frequency of a quantum of radiation that has 5.67 times 10 to the negative 21st joules of energy? This time, attack it the same way. The number has a unit of joules on it. Joules measures energy. So E equals 5.67 times 10 to the negative 21st joules. I'm all out of numbers, so I find what the question is asking for. What is the frequency? So I'm looking for V. And now I choose my equation. 2 equations there. C equals lambda V and E equals HV. Given my variables here, the only logical one to choose is E equals HV. Again, we'll list H. Over here, it's Planck's constant, 6.626 times 10 to the negative 34th joules seconds. Little different this time. I'm looking for frequency, which means I need that by itself. It currently is not, so we have to get it by itself by dividing away what's next to it. What I do to one side, I always have to do to the other according to math class. So those will cancel, and I'll get V is equal to E over Planck's constant. Before I plug in, I want to make sure that my units will match. I see joules seconds, I see joules. There are definitely 2 things in there that can cancel. So I plug in 5.67 times 10 to the negative 21st joules divided by 6.626 times 10 to the negative 34th joules seconds. Joules will cancel because it's on the top and the bottom. And if you notice, I have seconds in the bottom, which is 1 over seconds, which is the same as a hertz. And now we just do the math. 5.67 second E negative 21 divided by 6.626 second E negative 34. My calc says 8.557 times 10 to the negative positive 12. Watch your sig figs. 3 here, 4 here, right? Which means that if my number is 8.55791989, with 3 sig figs, yes, yes, yes. Will the 7 round the 5 up? It will. 8.56 times 10 to the 12th reciprocal seconds or hertz. So 2 pretty straightforward problems that are working with E equals HV. The last problem I'd like to show you is how we can link these 2 ideas together. It says, calculate the energy of a wave that has a wavelength of 2.50 times 10 to the negative 7th meters. We will try to solve this the same way we have all our other problems. First thing I see is this number. It has meters on it, and that measures wavelength. And if you remember, wavelength gets that goofy symbol lambda. 2.50 times 10 to the negative 7th meters. All out of numbers, so I look for what it's asking for. Calculate the energy. So I'm looking for energy. Next thing I would do is choose an equation. Here's where I run into a problem. because I only have two equations. E equals hv and C equals lambda v. Neither one of these equations has both E and lambda in it. This equation has lambda, this equation has E. Right? So what has to happen here is we need to decide which equation will get us to our final answer. And E is our question mark, which means this is our equation that we need to use. So we will have E equals hv. Here's the catch. We don't have v. We have the wavelength. So what's going on here is we have to do a problem in math class, right, called a substitution. This equation has v in it and what we know. So if I solve this equation for v, I can then plug it in. So we will solve this equation for our frequency, and then once we get it, plug it into our other equation to get our final answer. So let's do that. C equals lambda v. We want to solve that equation, which I'll call equation 1, for v. That means we divide both sides by lambda, and I'll get that v is equal to C over lambda. Right? If I'm listing things up here, all right, we have one equation, which means h needs to be around. So h is 6.626 times 10 to the negative 34th joules times seconds. I have a different equation that says that I need C, and C is equal to 3.00 times 10 to the 8th meters per second. So now I have everything that I need. I need C for this. It's right here. 3.00 times 10 to the 8th meters per second. I need my wavelength. I have it. 2.50 times 10 to the negative 7 meters. So do some math here. Meters cancels. I get hertz is my unit. And if we do our math, 3.00 second E8 divided by 2.50 second E negative 7, I will get a value of 1.20 times 10 to the 15th hertz. And this is V. Now I have the things that I need to plug into this equation. So I want to now solve the equation E equals hv for E, so we're good. H we know, 6.626 times 10 to the negative 34th joules seconds. And now V we solved for, and we are going to plug it in, the 1.20 times 10 to the positive 15th hertz will get plugged in there. Hertz and seconds will cancel, leaving me with joules. And now we do one more math problem to finish out. 6.626 second E negative 34 times 1.20 second E 15. I get a value of 7.5144 times 10 to the negative 19th. 3 sig figs here, 4 sig figs here, means this will be 7.51 times 10 to the negative 19 joules. So the trickiest of the problems, but it's not terribly unmanageable. We simply solve one equation and then substitute into the other equation because we need a piece of information that was not directly given to us. I hope this helped you out. If you have any other questions or confusion, please feel free to stop in for some help and ask questions.